My name's Randy Allen. I'm going to be your host this morning for the Technical Insights One track. First talk this morning is by Gianmarco Iodice, who's with ARM and who's going to be talking on performance analysis for optimizing embedded deep learning inference software. Those of you who have been around as long as I have know that the deep learning AI techniques have actually been around for a long time. What made it actually happen was getting compute power enough to be able to actually do it. Performance is always the key there. Gianmarco is going to be ones who's spending time on this, so it's a really interesting area to me.
Thanks a lot, Ronnie, for your introduction, and welcome everyone, and thanks a lot for coming to see this presentation, where I'm going to talk about performance analysis for deep learning software implementation on embedded devices. Or, in another way, how to give a meaning to our performance numbers in a deep learning scenario. So let's start to see the contents for this talk. In the first part of this presentation, I'm going to introduce the performance analysis problem for deep learning. In particular, I'm going to present the goals that we'd like to achieve with this presentation, along with a few matrices which will be used later on when I'm going to introduce a formal methodology for performance analysis. In particular, in the second and the third part of this talk, I'm going to introduce the top-down approach, which can be used to locate performance bottlenecks and also fix potential inefficiencies in our deep learning architecture. Of course, the topic is pretty big and maybe cannot fit as well in 1 hour presentation. I'll have and also maybe I'm going to simplify a few concepts. However, at the end of this presentation, you should have the fundamentals to carry out also even more complicated performance analysis for your specific processor type. So before continuing, I'd like just to spend just a few words for the company I work for. I work for ARM, and I'm responsible for the performance optimizations for the ARM compute library. So for whom doesn't know what ARM is a British semiconductor and software design company with headquarters in Cambridge, United Kingdom, and owned by SoftBank. Currently, ARM is leader in design architectures for CPUs and GPUs with a wide range of products like Cortex-A, Cortex-M, and Mali GPUs as well. So in this slide, I have reported a few numbers about ARM. I think the important numbers are over 90% of our smartphones are powered by an ARM processor. And the second aspect is ARM is currently number 1 on shipping mobile GPUs worldwide. But ARM is not just CPUs and GPUs. Now ARM is also ML. Because at ARM, we provide a set of free and open source software library highly optimized for CPUs and GPUs, like ARMNN and Compute Library, where I work on, but also a new class of processor type for machine learning. So if you'd like to have more information about this, you can visit our website where you can find all the information that you need. So I think we can start talking about performance analysis. And I'd like to start this presentation with a question. So let's assume we have the following networks, so SqueezeNet and MobileNet, and they run at 200 frames per second and 250 frames per second, respectively. What can we say about these numbers? So the answer is simple: nothing. We cannot say anything about these numbers because there are a lot of questions that I didn't answer before. For instance, what kind of data type are we using for these networks? But also, what kind of platform? What processor are we running on? What frequency? So there are a lot of questions. And without answering these questions, basically, we cannot say anything about these numbers. And the goal of this presentation is to give a meaning to these numbers, not just big or small, or it looks pretty good, but we want to understand if our performance are good on our specific processor type. But it's not enough because we want also a way to locate any performance bottlenecks in our deep learning architecture. And we want also a workflow to fix performance inefficiencies. Specifically for this talk, I'm going to present a workflow for fixing memory-bound inefficiencies in our architecture. Having in mind these goals, this means that we need to introduce a formal methodology to carry out our analysis in order to get significant performance boost. There are a few motivations behind this. So first of all, why would we like to introduce a formal methodology for performance analysis? Because we don't want a lucky or casual optimizations. So we don't like the approach, OK, let me try this algorithm and let's see if it works. Why we don't like that? Because we want to have controllability of our optimizations. We want to understand the effort. So let's assume we have an agile team. So we want a way to plan our optimizations in a shorter and longer term. But also, if we have a formal methodology, we can have a better understanding of our hardware capabilities. Because nowadays, in our system on chips, we can find a wide variety of processors on a single chip, like a CPU, like a GPU, a neural processing unit, or other processors. Okay? So we have different options to run the algorithm more efficiently in terms of power and in terms of speed of computation. So the situation is like that. So we have the deep neural network under test. And the output of the deep neural network is for us, for the performance analysis, the execution time or the frame per second. As I said, in order to give a meaning to our numbers, we need an approach. Okay? So we need to know the hardware capabilities and the number of operations required by my algorithm or my deep neural network architecture. Without knowing this information, we cannot say anything about the performance of my processor type. In terms of hardware capabilities, we all know the floating point operation per second, so which is usually expressed in terms of number of floating point operations per core and per cycle. But when we talk about deep learning, we can talk about more in general for operations per core per cycle, because not necessarily we have a floating point model. So we might have also quantized networks, for instance. Specifically for deep learning, we also talk about max per core per cycle, so the number of multiply accumulate operations per core and per cycle. In particular, if in hardware, we have the acceleration for that. This for what concerns the computational capabilities. But there is another important aspect to consider, which is related to the memory, which for this presentation has been simplified to a single bullet point. So, and essentially is the maximum memory bandwidth achievable by my platform, okay? So I'm aware that this is a simplistic way to express the memory bandwidth because we might have a memory hierarchy, so which means different memory bandwidth in my system on chip. But for this talk is enough to understand if my algorithms, for instance, might be limited by the memory transfer. Specifically for this talk, the maximum memory bandwidth considered is the bandwidth on the external memory, which in most of the cases is the DDR memory. What can we say about the computational complexity? So, as I said, we need an extra information. We need to know the number of operations required by my deep neural network. And this can be simply evaluated as a sum of the operations required by each layer of my architecture. This in general might be tricky, but for deep learning it's pretty simple because even if we require pre-knowledge of the algorithms involved, for deep learning are usually well-defined and also are mainly dominated by the multiply-accumulate operations in a convolution and a fully connected layer. So this means that, in theory, you need just to consider the number of multiply accumulate operations in your convolution layer and fully connected layers in order to have an estimation of the ops required by your network. Just one consideration. Remember that we like to give a meaning to our performance numbers. This means that if for a specific layer, for instance, a convolution, we can use different algorithms, let's say Winograd convolution layer, FFT, or a direct convolution approach, we have to use the ops of the algorithm deployed on for my network. Okay, so if we are using Winograd convolution layer, we should consider the number of operations required by the Winograd convolution. So we have everything, but we still need a way to understand if our numbers are good enough. And the way to understand this is through the processor utilization, so which expresses how well the algorithm uses the available computational resources on my processor. And the formula is pretty simple because it's the ratio between the theoretical execution time and the actual execution time. So the actual execution time is the execution time you evaluate for running your deep neural network. What about the theoretical execution time? Is the minimum time achievable by your processor for running your deep learning architecture. How can you evaluate that? It's pretty simple because we know everything. We know the ops required by the algorithm, so by the network, but also we know the hardware capabilities. So it's the ratio between the ops required by my network and the ops per core per cycle of my processor type, by the number of cores, by the frequency. So far, so good. So I managed to introduce a few metrics to understand if our performance are good. But now we need a formal methodology to understand, to locate performance bottlenecks and also fix potential performance inefficiencies. And the approach is called top-down approach, which is made up of different granular phases to find performance bottlenecks. What it means. So we have different level of profiling. And deeper we go in this pyramid, more information we can get to deliver even more optimizations. Okay? Let's start from the coarsest level of the pyramid, so at the top level. At the top level, we find the simplest way to profile my network. So I have only the information about the execution time of my graph. So this means that with the first level, we can only evaluate the execution time and the processor utilization for my graph. But we know that if we want to locate performance bottlenecks, we need to go one level below because we need the information about the layers or the execution time to run my layers and the functions involved in each layer. And the second level is called function profiling. At the deepest level of this pyramid, we can find the hardware counters profiling, which is not discussed in this presentation because it's processor-oriented. So it depends on which processor you're targeting. And also because this is mainly used by the backend developers, like, for instance, the Arman and guys. They use the hardware counters to profile the functions, like gem, to introduce extra optimizations. For this specific talk, we're going to use just two different, the first two levels of this pyramid, so graph profiling and function profiling. So what information we can get with these two profiling information? So let's assume we are running our network on a processor which is not a CPU. Okay, so it's the blue one. With the graph profiling, as I said, you can only evaluate the execution time for your graph. So we use the function profiling for calculating or estimating the execution time for my functions of my deep neural network. So if you pay attention to this slide, also there is an orange part, which is the time spent on the CPU. And why we have time spent on the CPU if you're running on another processor type? Because we might have an overhead introduced by the CPU for running your workload on a different processor type. For instance, you might have a driver overhead to dispatch the job on a GPU or a neural processing unit or a cache coherency. And also, the orange part of the overhead might increase if I profile my functions. However, fusing the information between the graph profiling and a function profiling, we can have an extra information, which is the overhead. The overhead introduced by the CPU in the graph profiling, which is the information that we want to evaluate. And it's simply the difference between the execution time of your graph and the sum of the execution time of each layer involved in your network. Before showing the workflow for fixing our performance inefficiencies, I need to introduce another concept, which is the memory bound. So essentially, we'd like to understand if our algorithms can be limited by the memory transfer. So the question is, how can we do it? There are a few models, like the roofline model, which can be used to estimate these. And this slide is an approximation of the roofline model. So essentially, we are trying to evaluate the bandwidth required by your algorithm. And how can we do it? So essentially, we need to evaluate the memory transfer per second required by your algorithm. So the total memory transfer read and write by the algorithm divided by the execution time to run it. If the execution time to run it is the theoretical execution time, which we have seen before is the minimum execution time to run your algorithm, we can have the maximum memory bandwidth for your specific algorithm. And this is important information because if we compare this number with the number I showed at the beginning, so the maximum memory bandwidth of your system, you can have an indication of if your layer might be limited by the memory transfer. So we have seen also the top-down approach, but I didn't show how these layers are linked together. So how we link the graph profiling to the function profiling and to the hardware counters profiling. And in the third and last session of this talk, I'm going to present a possible workflow to do that. Just a few general considerations before continuing. So in general, the matrix multiplication should be responsible for the largest portion of your overall execution time. So this means that the convolution layer should be the most expensive layer in your network. The second important thing to remark is this. So fully connected layer is memory bound because it's translated by a vector by matrix multiplication, which is memory bound. So this means that if your network has a lot of fully connected layer, the performance of your network might be limited by this because you can't beat the memory transfer. So the other thing is, how do we connect the profiling informations between the graph profiling, function profiling, and the hardware counters? With 3 phases. In the first phase, we want to estimate the process utilization for the graph, and we want to estimate the overhead as well. We know how to do it. But in the second phase, we want to understand if we have any memory-bound algorithms or layers in my networks. And we do the layer analysis for this reason. With the phase 3 instead, we try to debug our functions or our layers using the hardware counters. And since we need the hardware counters, this part is not discussed in this presentation. So we'll focus just on the phase 1 and phase 2. So let's start. So we have the graph profiling. So the only information we have at this point is the execution time for your graph, okay? Having the execution time of my graph, I can estimate the processor utilization. And I need to check if the process utilization is below or above the expectations. So the question might be, okay, what is my expectation? Well, it depends. You decide what is the expectation, or the harder guys decide for you. Okay, so we need to define a threshold. If the process utilization is above the expectation, or it is aligned with the expectation, it's fine. We don't require any extra work. Our network is optimized. Otherwise, the first step we need to do is the overhead evaluation. And we know how to evaluate this because we can merge the graph profiling with the function profiling for doing that. Also in this case, we evaluate the overhead with another threshold. And the threshold should be defined also by you. So if there are any mathematical formula to define the thresholds, you have to decide for your specific processor type what is the overhead. But if the overhead is below the expectation, the only way to fix it is to go through the hardware counters profiling in order to understand what is limiting or what is happening under the hood. So we do the overhead optimizations, and we start again the phase one in order to re-estimate the overhead introduced in my network. If the overhead is not my concern, we can go to the phase two, so to the layer analysis. So in the layer analysis, we are still at the function profiling level. So we have the execution time for each layer and execution time for each functions involved in each layer. So the first thing we can do is to collect this information in a table. So we can have the list of layers involved in my network, and I can report the percentage of the time spent by each layer, along with the process utilization for that. This is a real use case, and the use case reported is ResNet 12. Once we have this table, we need to remove some layers which basically don't require any further optimizations. And the first thing to do is, if the percentage of the time spent is negligible, I think we can remove it. For instance, we can remove activation functions from this list. Moreover, if the process utilization is above the expectations or is aligned with expectations, we can also remove from this list the layers that basically don't require any extra work. And the question is the list empty? If the list is empty, we go back to the phase one, and we start the evaluation. But since the list is not empty, as in this case, we proceed with the next slide, where we start the evaluation of the memory bandwidth. So for the two layers reported in this case, we have the last convolution layer of the ResNet 12, which has 8 gigaflops, 8 gigabytes per second, and the first convolution layer of the same network, which has 4 gigabytes per second. If we compare these numbers with the maximum memory bandwidth of the system reported in this case, we can maybe understand that maybe the convolution 12 is memory bounded. So the first question that we should ask to ourselves is it memory bound? Convolution 1, for instance, it doesn't look memory bounded. So in order to profile it, we need to proceed to the phase 3. And so this means that we require the hardware counters to understand what is happening there. But convolution 12 maybe is memory bound, or it is memory bound. So the question is, can we use a different algorithm for my layer? Since it is a convolution layer, we can think about using the FFT convolution. And in this specific case, if I recall correctly, we have 9 by 9 convolution with stride 1. So we try the FFT, and we change the algorithm and the ops accordingly. Because since we changed the algorithm for the convolution layer, we need to update the number of ops required by your deep neural network. Because otherwise, the number that the meaning that you give to the execution time is not correct. So we update the ops, and we go back to the phase 1. So in order to reevaluate the performance. But what does it happen if I don't have any other alternatives? So if I can't use a different algorithm? The only thing we can think about is, can we change the DNN design? So if we have a fully connected layer, maybe we have different alternatives. So we can try to remove it. If we cannot change the DNN design, we need to use, and once again, the phase 3 to understand if we can fix it. Otherwise, we update the design, we update the operation required, and we go back to the phase 1 once again. So we start again from the function profiling. So I have completed the workflow for detecting memory-bound or potential inefficiencies in our deep learning applications. And what are the key aspects behind this? So for sure, the top-down methodology helps a lot to find the deep neural network inefficiencies. I'm aware that most of the time we try to different algorithms, but we don't have a specific way to understand why we should use a different algorithm instead. So using this approach, we can find DNN inefficiencies easily, narrowing down the source of performance inefficiencies, in fact. The other thing is, in this presentation, I didn't talk about the hardware counter profiling because it is, as I said, processor-oriented. But with only two kinds of profiling informations, the graph and function profilings, we already have enough information to optimize our networks. The third and last aspect of this presentation is this. Knowing the computational capabilities of our processors, we can tweak our network to make the best use of our platform. Because remember that nowadays on our system on chips, especially on embedded system, we do not have only CPUs. We have a wide variety of processors. We have GPUs, we have neural processing unit, and if we know the capabilities of our processors, we can best fit our algorithm in the most efficient way. So I have completed my presentation, so thanks a lot for attending it.
So we have a couple of minutes for questions, if anyone has any. If you do, please go to the mic. In the meantime, I'm curious.
Yeah.
So do you have examples? Do you have specific examples of, it's a great methodology. Can you provide us with concrete examples of the performance improvements you've gotten by applying it?
Yes. So the example I reported in this slide is related to ResNet 12. Simply changing the FFT using this approach, we were able to improve the performance of 40% of 40%. These numbers is also reflected in the latest ARM Compute Library release, which will be released soon. And yes, we use this approach for fixing it. We had a significant speed up, simply changing different algorithm.
Okay. Over here.
Thank you for your presentation. So my question is, when you deal with the memory-bound issues, is also the data type involved? So if you change the data type from floating point 32 to, say, unsigned or signed 8-bit, is the memory bandwidth kind of boundary restricting a little bit? Or?
So essentially, first of all, thanks for your question. But yes, so the maximum memory bandwidth of your system is still the same. So you know the hardware capabilities. Of course, why we use quantized networks, also for overcoming this problem. So trying to avoid any memory-bound issues in my system. Of course, reducing the data type, so using, for instance, int8 or signed 8-bit data types, we can reduce the amount of memory needed by my convolution layers, and then maybe we can improve the performance as well for this reason. So yes.
Okay, last question over here.
Thank you very much for presentation. I'm not very familiar with Mali GPU, so my question is, does ARM make public the performance information for Mali GPU for popular DNNs such as MobileNet, ResNet, and so forth? Does ARM make public that information that basically you talked about today?
So if you are talking about relative performance improvement, the answer is yes. So for instance, recently, last week, I published a blog post where I reported the performance improvements for Mali GPUs and also for Cortex-A CPUs for different networks and also different data types as well. So in terms of relative performance, yes. We try to give an update in terms of what is the expectations in terms of networks and in terms of improvements. So yes.
And is that information available on ARM websites?
Yes, the information is available on the ARM website and also on our community, developer community. So there are a few blogs reporting the performance improvements, for instance, for the ARM compute library.
Okay, so let me remind you that feedback's very important to the Embedded Vision Alliance. So if you would fill out a speaker survey before you leave, and you've got a chance of winning a $100 Amazon gift card in addition to doing that. So always good to do it while you're remembering. With that, let's thank our speaker once again. And
thanks a lot.